All the experiences in your life, from single conversations to your broader culture, shape the microscopic details of your brain. Neurally speaking, who you are depends on where you've been. Your brain is a relentless shapeshifter, constantly rewriting its own circuitry, and because your experiences are unique, so are the vast, detailed patterns in your neural networks. Because they continue to change your whole life, your identity is a moving target, it never reaches an endpoint. Although neuroscience is my daily routine, I'm still in awe every time I hold a human brain. After you take into account its substantial weight, an adult brain weighs in at 3 pounds, its strange consistency, like firm jelly, and its wrinkled appearance, deep valleys carving a puffy landscape. What's striking is the brain's sheer physicality. This hunk of unremarkable stuff seems so at odds with the mental processes it creates. Our thoughts and our dreams, our memories and experiences all arise from this strange neural material. Who we are is found within its intricate firing patterns of electrochemical pulses. When that activity stops, so do you. When that activity changes character, due to injury or drugs, you change character in lockstep. Unlike any other part of your body, if you damage a small piece of the brain, who you are is likely to change radically. To understand how this is possible, let's start at the beginning. Born unfinished. At birth we humans are helpless. We spend about a year unable to walk, about 2 more before we can articulate full thoughts, and many more years unable to fend for ourselves. We are totally dependent on those around us for our survival. Now compare this to many other mammals. Dolphins, for instance, are born swimming. Giraffes learn to stand within hours. A baby zebra can run within 45 minutes of birth. Across the animal kingdom, our cousins are strikingly independent soon after they're born. On the face of it, that seems like a great advantage for other species, but in fact it signifies a limitation. Baby animals develop quickly because their brains are wiring up according to a largely pre-programmed routine. But that preparedness trades off with flexibility. Imagine if some hapless rhinoceros found itself on the Arctic tundra, or on top of a mountain in the Himalayas, or in the middle of urban Tokyo. It would have no capacity to adapt, which is why we don't find rhinos in those areas. This strategy of arriving with a prearranged brain works inside a particular niche in the ecosystem, but put an animal outside of that niche, and its chances of thriving are low. In contrast, humans are able to thrive in many different environments, from the frozen tundra to the high mountains to bustling urban centers. This is possible because the human brain is born remarkably unfinished. Instead of arriving with everything wired up, let's call it hardwired, a human brain allows itself to be shaped by the details of life experience. This leads to long periods of helplessness as the young brain slowly molds to its environment. It's live-wired childhood pruning, exposing the statue in the marble. What's the secret behind the flexibility of young brains? It's not about growing new cells. In fact, the number of brain cells is the same in children and adults. Instead, the secret lies in how those cells are connected. At birth, a baby's neurons are disparate and unconnected, and in the first 2 years of life they begin connecting up extremely rapidly as they take in sensory information. As many as 2 million new connections, or synapses, are formed every second in an infant's brain. By age 2, a child has over 100 trillion synapses, double the number an adult has. LIWIRNG. Many animals are born genetically pre-programmed, or hardwired for certain instincts and behaviors. Genes guide the construction of their bodies and brains in specific ways that define what they will be and how they'll behave. A fly's reflex to escape in the presence of a passing shadow, a robin's pre-programmed instinct to fly south in the winter, a bear's desire to hibernate, a dog's drive to protect its master. These are all examples of instincts and behaviors that are hardwired. Hardwiring allows these creatures to move as their parents do from birth, and in some cases to eat for themselves and survive independently. In humans the situation is somewhat different. The human brain comes into the world with some amount of genetic hardwiring, for example, for breathing, crying, suckling, caring about faces, and having the ability to learn the details of their native language. But compared to the rest of the animal kingdom, human brains are unusually incomplete at birth. The detailed wiring diagram of the human brain is not pre-programmed. Instead, genes give very general directions for the blueprints of neural networks, and world experience fine-tunes the rest of the wiring, allowing it to adapt to the local details. The human brain's ability to shape itself to the world into which it's born has allowed our species to take over every ecosystem on the planet and begin our move into the solar system. It has now reached a peak and has far more connections than it will need. At this point, the blooming of new connections is supplanted by a strategy of neural pruning. As you mature, 50% of your synapses will be pared back. Which synapses stay and which go? When a synapse successfully participates in a circuit, it is strengthened. In contrast, synapses weaken if they aren't useful, and eventually they are eliminated. Just like paths in a forest, you lose the connections that you don't use. In a sense, the process of becoming who you are is defined by carving back the possibilities that were already present. You become who you are not because of what grows in your brain, but because of what is removed. Throughout our childhoods, our local environments refine our brain, taking the jungle of possibilities and shaping it back to correspond to what we're exposed to. Our brains form fewer but stronger connections. As an example, the language that you're exposed to in infancy, say, English versus Japanese, refines your ability to hear the particular sounds of your language, and worsens your capacity to hear the sounds of other languages. That is, a baby born in Japan and a baby born in America can hear and respond to all the sounds in both languages. Through time, the baby raised in Japan will lose the ability to distinguish between, say, the sounds of R and L, two sounds that aren't separated in Japanese. We are sculpted by the world we happen to drop into. Nature's gamble. Over our protracted childhood, the brain continually pairs back its connections, shaping itself to the particulars of its environment. This is a smart strategy to match a brain to its environment, but it also comes with risks. If developing brains are not given the proper, expected environment, one in which a child is nurtured and looked after, the brain will struggle to develop normally. This is something the Jensen family from Wisconsin has experienced firsthand. Carol and Bill Jensen adopted Tom, John, and Victoria when the children were 4 years old. The 3 children were orphans who had, until their adoption, endured appalling conditions in state-run orphanages in Romania, with consequences for their brain development. When the Jensens picked up the children and took a taxi out of Romania, Carol asked the taxi driver to translate what the children were saying. The taxi driver explained they were speaking gibberish. It was not a known language, starved of normal interaction. The children had developed a strange Creole. As they've grown up, the children have had to deal with learning disabilities, the scars of their childhood deprivation. Tom, John, and Victoria don't remember much about their time in Romania. In contrast, someone who remembers the institutions vividly is Dr. Charles Nelson, professor of pediatrics at Boston Children's Hospital. He first visited these institutions in 1999. What he saw horrified him. Young children were kept in their cribs, with no sensory stimulation. There was a single caretaker for every 15 children, and these workers were instructed not to pick the children up or show them affection in any way, even when they were crying. The concern was that such displays of affection would lead to the children wanting more, an impossibility with the limited staffing. In this context, things were as regimented as possible. Children were lined up on plastic pots for toileting. Everyone got the same haircut, regardless of gender. They were dressed alike, fed on schedule. Everything was mechanized. Children whose cries went unanswered soon learned not to cry. The children were not held and were not played with. Although they had their basic needs met, they were fed, washed and clothed. The infants were deprived of emotional care, support, and any kind of stimulation. As a result, they developed indiscriminate friendliness. Nelson explains that he'd walk into a room and be surrounded by little kids he'd never seen before, and they'd want to jump into his arms and sit on his lap or hold his hand or walk off with him. Although this sort of indiscriminate behavior seems sweet at first glance, it's a coping strategy of neglected children, and it goes hand in hand with long-term attachment issues. It is a hallmark behavior of children who have grown up in an institution. Shaken by the conditions they were witnessing, Nelson and his team set up the Bucharest Early Intervention Program. They assessed 136 children, aged 6 months to 3 years, who had been living in institutions from birth. First, it became clear that the children had IQs in the 60s and 70s, compared to an average of 100. The children showed signs of underdeveloped brains and their language was very delayed. When Nelson used electroencephalography, EEG, to measure the electrical activity in these children's brains, he found they had dramatically reduced neural activity. ROMANIASORPHANAGES. In 1966, to increase the population and the workforce, Romanian President Nicolae Ceausescu banned contraception and abortion. State gynecologists, known as menstrual police, examined women of childbearing age to ensure they were producing enough offspring. A celibacy tax was levied on families who had fewer than 5 children. The birth rate skyrocketed. Many poor families couldn't afford to care for their children, and so they gave them over to state-run institutions. In turn, the state rolled out more institutions to meet the soaring numbers. By 1989, when Ceausescu was ousted, 170,000 abandoned children resided in institutions. Scientists soon revealed the consequences of an institutional upbringing on brain development. And those studies influenced government policy. Over the years, most of the Romanian orphans have been returned to their parents or removed to government foster care. By 2005, Romania made it illegal for children to be institutionalized before the age of 2, unless severely disabled. Millions of orphans still live in institutionalized government care around the world. Given the necessity of a nurturing environment for an infant's developing brain, it is imperative that governments find ways to get the children into conditions that allow proper brain development. Without an environment with emotional care and cognitive stimulation, the human brain cannot develop normally. Encouragingly, Nelson's study also revealed an important flip side: the brain can often recover, to varying degrees, once the children are removed to a safe and loving environment. The younger a child is removed, the better his recovery. Children removed to foster homes before the age of 2 generally recovered well. After 2, they made improvements, but depending on the age of the child they were left with differing levels of developmental problems. Nelson's results highlight the critical role of a loving, nurturing environment for a developing child's brain. And this illustrates the profound importance of the environment around us in shaping who we become. We are exquisitely sensitive to our surroundings. Because of the wire-on-the-fly strategy of the human brain, who we are depends heavily on where we've been. The teen years. Only a couple of decades ago it was thought that brain development was mostly complete by the end of childhood. But we now know that the process of building a human brain takes up to 25 years. The teen years are a period of such important neural reorganization and change that it dramatically affects who we seem to be. Hormones coursing around our bodies cause obvious physical changes as we take on the appearance of adults, but out of sight our brains are undergoing equally monumental changes. These changes profoundly color how we behave and react to the world around us. One of these changes has to do with an emerging sense of self, and with it, self-consciousness. To get a sense of the teen brain at work, we ran a simple experiment. With the help of my graduate student Ricky Savjani, we asked volunteers to sit on a stool in a shop window display. We then pulled back the curtain to expose the volunteer looking out on the world, to be gawked at by passers-by. Before sending them into this socially awkward situation, we rigged up each volunteer so we'd be able to measure their emotional response. We hooked them up with a device to measure the galvanic skin response, GSR, a useful proxy for anxiety. The more your sweat glands open, the higher your skin conductance will be. This is, by the way, the same technology used in a lie detector, or polygraph test. Both adults and teens participated in our experiment. In adults, we observed a stress response from being stared at by strangers, exactly as expected. But in teenagers, that same experience caused social emotions to go into overdrive. The teens were much more anxious, some to the point of trembling, while they were being watched. Why the difference between the adults and teens? The answer involves an area of the brain called the medial prefrontal cortex, MPFC. This region becomes active when you think about yourself, and especially the emotional significance of a situation to yourself. Dr. Leah Somerville and her colleagues at Harvard University found that as one grows from childhood to adolescence, the MPFC becomes more active in social situations, peaking at around 15 years old. At this point, social situations carry a lot of emotional weight, resulting in a self-conscious stress response of high intensity. That is, in adolescence, thinking about oneself, so-called self-evaluation, is a high priority. In contrast, an adult brain has grown accustomed to a sense of self, like having broken in a new pair of shoes, and as a result an adult doesn't care as much about sitting in the shop window. SCULPT in GOFTHEADOLESCENTBRA in. After childhood, just before the onset of puberty, there is a second period of overproduction. The prefrontal cortex sprouts new cells and new connections, synapses, thereby creating new pathways for molding. This excess is followed by approximately a decade of pruning, all through our teenage years. Weaker connections are trimmed back while stronger connections are reinforced. As a result of this thinning out, the volume of the prefrontal cortex reduces by about 1% per year during the teenage years. The shaping of circuits during the teen years sets us up for the lessons we learn on our paths to Becoming adults. Because these massive changes take place in brain areas required for higher reasoning and the control of urges, adolescence is a time of steep cognitive change. The dorsolateral prefrontal cortex, important for controlling impulses, is among the most belated regions to mature, not reaching its adult state until the early 20s. Well before neuroscientists worked out the details, car insurance companies noticed the consequences of incomplete brain maturation, and they accordingly charge more for teen drivers. Likewise, the criminal justice system has long held this intuition, and thus juveniles are treated differently than adults. Beyond social awkwardness and emotional hypersensitivity, the teen brain is set up to take risks. Whether it's driving fast or sexting naked photos, risky behaviors are more tempting to the teen brain than to the adult brain. Much of that has to do with the way we respond to rewards and incentives. As we move from childhood into adolescence, the brain shows an increasing response to rewards in areas related to pleasure seeking. One such area is called the nucleus accumbens. In teens, the activity here is as high as it is in adults. But here's the important fact: activity in the orbitofrontal cortex, involved in executive decision-making, attention, and simulating future consequences, is still about the same in teens as it is in children. A mature pleasure-seeking system coupled with an immature orbitofrontal cortex means that teens are not only emotionally hypersensitive, but also less able to control their emotions than adults. Moreover, Somerville and her team have an idea why peer pressure strongly compels behavior in teens. Areas involved in social considerations, such as the MPFC, are more strongly coupled to other brain regions that translate motivations into actions, the striatum and its network of connections. This, they suggest, might explain why teens are more likely to take risks when their friends are around. How we see the world as a teenager is the consequence of a changing brain that's right on schedule. These changes lead us to be more self-conscious, more risk-taking, and more prone to peer-motivated behavior. For frustrated parents the world over, there's an important message: who we are as a teenager is not simply the result of a choice or an attitude, it is the product of a period of intense and inevitable neural change. Plasticity in adulthood. By the time we're 25 years of age, the brain transformations of childhood and adolescence are finally over. The tectonic shifts in our identity and personality have ended, and our brain appears to now be fully developed. You might think that who we are as adults is now fixed in place, immovable. But it's not. In adulthood our brains continue to change. Something that can be shaped, and can hold that shape, is what we describe as plastic. And so it is with the brain. Even in adulthood, experience changes it, and it retains the change. To get a sense of how impressive these physical changes can be, consider the brains of a particular group of men and women who work in London, the city's cab drivers. They undergo 4 years of intensive training to pass the knowledge of London, one of society's most difficult feats of memory. The knowledge requires aspiring cabbies to memorize London's extensive roadways, in all their combinations and permutations. This is an exceedingly difficult task. The knowledge covers 320 different routes through the city, 25,000 individual streets, and 20,000 landmarks and points of interest, hotels, theaters, restaurants, embassies, police stations, sports facilities, and anywhere a passenger is likely to want to go. Students of the knowledge typically spend 3 to 4 hours a day reciting theoretical journeys. The unique mental challenges of the knowledge sparked the interest of a group of neuroscientists from University College London, who scanned the brains of several cab drivers. The scientists were particularly interested in a small area of the brain called the hippocampus, vital for memory, and, in particular, spatial memory. The scientists discovered visible differences in the cabbies' brains. In the drivers, the posterior part of the hippocampus had grown physically larger than those in the control group, presumably causing their increased spatial memory. The researchers also found that the longer a cabbie has been doing his job, the bigger the change in that brain region, suggesting that the result was not simply reflecting a pre-existing condition of people who go into the profession, but instead resulted from practice. The cab driver study demonstrates that adult brains are not fixed in place, but instead can reconfigure so much that the change is visible to the trained eye. It's not just cab drivers whose brains reshape themselves. When one of the most famous brains of the 20th century was examined, Albert Einstein's brain did not reveal the secret of his genius. But it did show that the brain area devoted to his left fingers had expanded, forming a giant fold in his cortex called the omega sign, shaped like the Greek symbol, all thanks to his less commonly known passion for playing the violin. This fold becomes enlarged in experienced violin players, who intensively develop fine dexterity with the fingers of their left hand. Piano players, in contrast, develop an omega sign in both hemispheres, as they use both hands in fine, detailed movements. The shape of the hills and valleys in the brain is largely conserved across people, but the finer details give a personal and unique reflection of where you've been and who you are now. Although most of the changes are too small to detect with the naked eye, everything you've experienced has altered the physical structure of your brain, from the expression of genes to the positions of molecules to the architecture of neurons. Your family of origin, your culture, your friends, your work, every movie you've watched, every conversation you've had, these have all left their footprints in your nervous system. These indelible, microscopic impressions accumulate to make you who you are, and to constrain who you can become. Pathological changes. Changes in our brain represent what we've done and who we are. But what happens if the brain changes because of a disease or injury? Does this also alter who we are, our personalities, our actions? On August 1, 1966, Charles Whitman took an elevator to the observation deck of the University of Texas Tower in Austin. Then the 25-year-old started firing indiscriminately at people below. 13 people were killed and 33 wounded, until Whitman himself was finally shot dead by police. When they got to his house, they discovered that he had killed his wife and mother the night before. There was only one thing more surprising than this random act of violence, and that was the lack of anything about Charles Whitman that would seem to have predicted it. He was an Eagle Scout, he was employed as a bank teller, and he was an engineering student. Shortly after killing his wife and his mother, he'd sat down and typed what amounted to a suicide note. I don't really understand myself these days. I am supposed to be an average, reasonable and intelligent young man. However, lately, I cannot recall when it started. I have been a victim of many unusual and irrational thoughts. After my death, I wish that an autopsy would be performed on me to see if there is any visible physical disorder. Whitman's request was granted. After an autopsy, the pathologist reported that Whitman had a small brain tumor. It was about the size of a nickel, and it was pressing against a part of his brain called the amygdala, which is involved in fear and aggression. This small amount of pressure on the amygdala led to a cascade of consequences in Whitman's brain, resulting in him taking actions that would otherwise be completely out of character. His brain matter had been changing, and who he was changed with it. This is an extreme example, but less dramatic changes in your brain can alter the fabric of who you are. Consider the ingestion of drugs or alcohol. Particular kinds of epilepsy make people more religious. Parkinson's disease often makes people lose their faith. While the medication for Parkinson's can often turn people into compulsive gamblers. It's not just illness or chemicals that change us, from the movies we watch to the jobs we work, everything contributes to a continual reshaping of the neural networks we summarize as us. So who exactly are you? Is there anyone down deep, at the core? Am I the sum of my memories? Our brains and bodies change so much during our life that, like a clock's hour hand, it's difficult to detect the changes. Every 4 months your red blood cells are entirely replaced, for instance, and your skin cells are replaced every few weeks. Within about 7 years every atom in your body will be replaced by other atoms. Physically, you are constantly a new you. Fortunately, there may be one constant that links all these different versions of yourself together: memory. Perhaps memory can serve as the thread that makes you who you are. It sits at the core of your identity, providing a single, continuous sense of self. But there might be a problem here. Could the continuity be an illusion? Imagine you could walk into a park and meet yourself at different ages in your life. There you are, aged 6, as a teenager, in your late 20s, mid-50s, early 70s, all the way through your final years. In this scenario, you could all sit together and share the same stories about your life, teasing out the single thread of your identity. Or could you? You all possess the name and history, but the fact is that you're all somewhat different people, in possession of different values and goals. And your lives' memories might have less in common than expected. Your memory of who you were at 15 is different to who you actually were at 15, moreover, you'll have different memories that relate back to the same events. Why? Because of what a memory is, and isn't. Rather than memory being an accurate video recording of a moment in your life, it is a fragile brain state from a bygone time that must be resurrected for you to remember. Here's an example: you're at a restaurant for a friend's birthday. Everything you experience triggers particular patterns of activity in your brain. For example, there's a particular pattern of activity sparked into life by the conversation between your friends. Another pattern is activated by the smell of the coffee, yet another by the taste of a delicious little French cake. The fact that the waiter puts his thumb in your cup is another memorable detail, represented by a different configuration of neurons firing. All of these constellations become linked with one another in a vast associative network of neurons that the hippocampus replays, over and over, until the associations become fixed. The neurons that are active at the same time will establish stronger connections between them, cells that fire together, wire together. The resulting network is the unique signature of the event, and it represents your memory of the birthday dinner. Now let's imagine that 6 months later you taste one of those little French cakes, just like the one you tasted at the birthday party. This very specific key can unlock the whole web of associations. The original constellation lights up, like the lights of a city switching on. And suddenly you're back in that memory. Although we don't always realize it, the memory is not as rich as you might have expected. You know that your friends were there. He must have been wearing a suit, because he always wears a suit. And she was wearing a blue shirt. Or maybe it was purple. It might have been green. If you really probe the memory, you'll realize that you can't remember the details of any of the other diners at the restaurant, even though the place was full. So your memory of the birthday meal has started to fade. Why? For a start, you have a finite number of neurons, and they are all required to multitask. Each neuron participates in different constellations at different times. Your neurons operate in a dynamic matrix of shifting relationships, and heavy demand is continually placed on them to wire with others. So your memory of the birthday dinner has become muddled, as those birthday neurons have been co-opted to participate in other memory networks. The enemy of memory isn't time, it's other memories. Each new event needs to establish new relationships among a finite number of neurons. The surprise is that a faded memory doesn't seem faded to you. You feel, or at least assume, that the full picture is there. And your memory of the event is even more dubious. Say that in the intervening year, since the dinner, your two friends have split up. Thinking back on the dinner, you might now misremember sensing red flags. Wasn't he more quiet than usual that night? Weren't there moments of awkward silence between the two? Well, it will be difficult to know for certain, because the knowledge that's in your network now changes the memory that corresponds to then. You can't help but have your present color your past. So a single event may be perceived somewhat differently by you at different stages in your life. The fallibility of memory. Clues to the malleability of our memory come from the pioneering work of Professor Elizabeth Loftus at University of California, Irvine. She transformed the field of memory research by showing how susceptible memories are. Loftus devised an experiment in which she invited volunteers to watch films of car crashes, and then asked them a series of questions to test what they remembered. The questions she asked influenced the answers she received. She explains, when I asked, how fast were the cars going when they hit each other, versus how fast were the cars going when they smashed into each other, witnesses give different estimates of speed. They thought the cars were going faster when I used the word smashed. Intrigued by the way that leading questions could contaminate memory, she decided to go further. Would it be possible to implant entirely false memories? To find out, she recruited a selection of participants, and had her team contact their families to get information about events in their past. Armed with this information, the researchers put together 4 stories about each participant's childhood. 3 were true. The 4th story contained plausible information, but was entirely made up. The 4th story was about getting lost in a shopping mall as a child, being found by a kind elderly person, and finally being reunited with a parent. In a series of interviews, participants were told the 4 stories. At least a quarter claimed they could remember the incident of being lost in the mall, even though it hadn't actually happened. And it didn't stop there. Loftus explains, they may start to remember a little bit about it. But when they come back a week later, they're starting to remember more. Maybe they'll talk about the older woman who rescued them. Over time, more and more detail crept into the false memory. The old lady was wearing this crazy hat, I had my favorite toy with me, my mom was so mad. So not only was it possible to implant false new memories in the brain, but people embraced and embellished them, unknowingly weaving fantasy into the fabric of their identity. We're all susceptible to this memory manipulation, even Loftus herself. As it turns out, when Elizabeth was a child, her mother had drowned in a swimming pool. Years later, a conversation with a relative brought out an extraordinary fact, that Elizabeth had been the one to find her mother's body in the pool. That news came as a shock to her. She hadn't known that, and in fact she didn't believe it. But, she describes, I went home from That birthday, and I started to think, maybe I did. I started to think about other things that I did remember, like when the firemen came, they gave me oxygen. Maybe I needed the oxygen cause I was so upset that I found the body. Soon, she could visualize her mother in the swimming pool. But then her relative called to say he had made a mistake. It wasn't the young Elizabeth, after all, who had found the body. It had been Elizabeth's aunt. And that's how Loftus had the opportunity to experience what it was like to possess her own false memory, richly detailed and deeply felt. Our past is not a faithful record. Instead, it's a reconstruction, and sometimes it can border on mythology. When we review our life memories, we should do so with the awareness that not all the details are accurate. Some came from stories that people told us about ourselves, others were filled in with what we thought must have happened. So if your answer to who you are is based simply on your memories, that makes your identity something of a strange, ongoing, mutable narrative. The aging brain. Today we're living longer than at any point in human history, and this presents challenges for maintaining brain health. Diseases like Alzheimer's and Parkinson's attack our brain tissue, and with it, the essence of who we are. But here's the good news: in the same way that your environment and behavior shape your brain when you're younger, they are just as important in your later years. Memoryofthefuture. Henry Molaison suffered his first major epileptic seizure on his 15th birthday. From there, the seizures grew more frequent. Faced with a future of violent convulsions, Henry underwent an experimental surgery, one which removed the middle part of the temporal lobe, including the hippocampus, on both sides of his brain. Henry was cured of the seizures, but with a dire side effect: for the rest of his life, he was unable to establish any new memories. But the story doesn't end there. Beyond his inability to form new memories, he was also unable to imagine the future. Picture what it would be like to go to the beach tomorrow. What do you conjure up? Surfers and sandcastles? Crashing waves? Rays of sun breaking through clouds? If you were to ask Henry what he might imagine, a typical response might be, "All I can come up with is the color blue." His misfortune reveals something about the brain mechanisms that underlie memory. Their purpose is not simply to record what has gone before, but to allow us to project forward into the future. To imagine tomorrow's experience at the beach. The hippocampus, in particular, plays a key role in assembling an imagined future by recombining information from our past. Across the U.S., more than 1,100 nuns, priests, and brothers have been taking part in a unique research project, the Religious Orders Study, to explore the effects of aging on the brain. In particular, the study is interested in teasing out the risk factors for Alzheimer's disease, and it includes subjects, aged 65 and over, who are symptom-free and don't exhibit any measurable signs of disease. Keeping a busy lifestyle into old age benefits the brain. In addition to being a stable group that can be easily tracked down each year for regular tests, the religious orders share a similar lifestyle, including nutrition and living standards. This allows for fewer so-called confounding factors, or differences, that might arise in the wider population, like diet, or socioeconomic status or education, all of which could interfere with the study results. Data collection began in 1994. So far, Dr. David Bennett and his team at Rush University in Chicago have collected over 350 brains. Each one is carefully preserved, and examined for microscopic evidence of age-related brain diseases. And that's only half the study. The other half involves the collection of in-depth data on each participant while They're alive. Every year, everyone in the study undergoes a battery of tests, ranging from psychological and cognitive appraisals to medical, physical, and genetic tests. Hundreds of nuns have donated their brains for examination after their death. Researchers were caught off guard by the results. When the team began their research, they expected to find a clear-cut link between cognitive decline and the three diseases that are the most common causes of dementia: Alzheimer's, stroke and Parkinson's. Instead, here's what they found: having brain tissue that was being riddled with the ravages of Alzheimer's disease didn't necessarily mean a person would experience cognitive problems. Some people were dying with a full-blown Alzheimer's pathology without having cognitive loss. What was going on? The team went back to their substantial data sets for clues. Bennett found that psychological and experiential factors determined whether there was loss of cognition. Specifically, cognitive exercise, that is, activity that keeps the brain active, like crosswords, reading, driving, learning new skills, and having responsibilities, was protective. So were social activity, social networks and interactions, and physical activity. On the flip side, they found that negative psychological factors like loneliness, anxiety, depression, and proneness to psychological distress were related to more rapid cognitive decline. Positive traits like conscientiousness, purpose in life, and keeping busy were protective. The participants with diseased neural tissue, but no cognitive symptoms, have built up what is known as cognitive reserve. As areas of brain tissue have degenerated, other areas have been well exercised, and therefore have compensated or taken over those functions. The more we keep our brains cognitively fit, typically by challenging them with difficult and novel tasks, including social interaction, the more the neural networks build new roadways to get from A to B. Think of the brain like a toolbox. If it's a good toolbox, it will contain all the tools you need to get a job done. If you need to disengage a bolt, you might fish out a ratchet. If you don't have access to the ratchet, you'll pull out a wrench. If the wrench is missing, you might try a pair of pliers. It's the same concept in a cognitively fit brain. Even if many pathways degenerate because of disease, the brain can retrieve other solutions. The nuns' brains demonstrate that it's possible to protect our brains, and to help hold onto who we are for as long as possible. We can't stop the process of aging, but by practicing all the skills in our cognitive toolbox, we may be able to slow it down. I am sentient. When I think about who I am, there's one aspect above all that can't be ignored: I am a sentient being. I experience my existence. I feel like I'm here, looking out on the world through these eyes, perceiving this technicolor show from my own center stage. Let's call this feeling consciousness or awareness. Scientists often debate the detailed definition of consciousness, but it's easy enough to pin down what we're talking about with the help of a simple comparison. When you're awake, you have consciousness, and when you're in deep sleep, you don't. That distinction gives us an inroad for a simple question: what is the difference in brain activity between those two states? One way to measure that is with electroencephalography, EEG, which captures a summary of billions of neurons firing by picking up weak electrical signals on the outside of the skull. It's a bit of a crude technique. Sometimes it's compared to trying to understand the rules of baseball by holding a microphone against the outside of a baseball stadium. Nonetheless, EEG can offer immediate insights into the differences between the waking and sleeping states. When you're awake, your brain waves reveal that your billions of neurons are engaged in complex exchanges with one another. Think of it like thousands of individual conversations in the ballgame crowd. When you go to sleep, your body seems to shut down. So it's a natural assumption that the neuronal stadium quiets down. But in 1953 it was discovered that such an assumption is incorrect. The brain is just as active at night as during the day. During sleep, neurons simply coordinate with one another differently, entering a more synchronized, rhythmic state. Imagine the crowd at the stadium doing an incessant Mexican wave, around and around. Consciousness emerges when neurons are coordinating with one another in complex, subtle, mostly independent rhythms. In slow-wave sleep, neurons are more synchronized with one another, and consciousness is absent. As you can imagine, the complexity of the discussion in a stadium is much richer when thousands of discrete conversations are playing out. In contrast, when the crowd is entrained in a bellowing wave, it's a less intellectual time. So who you are at any given moment depends on the detailed rhythms of your neuronal firing. During the day, the conscious you emerges from that integrated neural complexity. At night, when the interaction of your neurons changes just a bit, you disappear. Your loved ones have to wait until the next morning, when your neurons let the wave die and work themselves back into their complex rhythm. Only then do you return.